All right, this is Oceans Part 2, where we are going to be learning about the movement in the ocean, such as currents. We're going to look at seashore movement. We're going to look at how sedimentation occurs, how the erosion of our shores work, how water is moved, and how it can even affect our climate, which is cool. So currents are masses of water that essentially flow from one place to the other, right? The biggest ones are gyres and surface currents. We all should know both, but surface currents have to do with wind and friction on the surface of the water. So they are entirely dependent on wind movement. Whereas gyres are also known as boundary currents. These are related to atmospheric circulation, and these are massive, slow-moving currents that go from north to south. And there are 5 main gyres. You have the North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian Ocean gyre. So the cool thing about these gyres is that they will come from the equatorial region where it is hot, and they'll go all the way up to the Arctic and Antarctic where it is cold. Okay, and this affects the water temperature in the gyre itself. So what ends up happening is we start in the equatorial area, which, if we notice, starts for the North Atlantic gyre off the coast of Africa, which makes sense as to this is the direction that our hurricanes go, correct? Yes. Aha. So we're going to have warm water come up in here through the Gulf, which explains why the Gulf is always so warm. And then it's going to go up along the east coast of the United States, which we call the Gulf Stream. Okay. The Gulf Stream itself is warm, and as it moves up, particularly in summer when it gets nice and warm, up in the northern areas, the ocean can get up to close to 80 degrees by the end of summer, and by the end of summer, I mean like August, September. Yes, I know, this sounds awful, but in the beginning of summer, it can be 50-degree water, so which would you choose? We choose both, because we like to go to the beach in the summer. Anyway, so once you get up here, you're going to see this kind of split off in multiple ways. The Norwegian current will come up north, and it will actually change and come back down cold, which will then go past England, the coast of France, and then back along the northern coast of Africa, and it will warm up and go back and start all around. So this is why we have very different environments off the west coast in Europe versus the east coast in America. Okay, so our summers are hot. Sometimes they're humid. Over, for example, in London, France, and Ireland, you may get warm summers, but it's going to be relatively cool. You're going to have rain in the winter, and very foggy in the winter and fall, because that's eventually when that warmer water is finally going to get over there. But generally, the oceans over here are pretty cold. The English Channel is always notoriously freezing. And this affects all these different areas. So here we have hot water, and this explains over here, which is we have tropical rainforests, versus on this side we have a lot of desert because it is so cold. We also see the same thing on this coast, where it gets quite cold on our west coast with the water, and it is pretty dry over there. They have a lot of fog. They're going to have desert areas. California doesn't get a lot of rain. Okay, this is all because of the California current. And of course, the West Australian current over here is all desert. These two do counteract with each other. You are going to see a lot of desert in Australia, but this side of Australia is pretty warm, which is cool. And that is because of the EAC, which we all know about, right? Yeah. So these currents are related to atmospheric circulation, and that is just because of how the water itself will affect the weather that is around it. So, for example, in our summer, it is very humid. You can essentially swim through the air. You have a lot of thunderstorms. It's very wet. We have the Everglades. But if you go over to Texas, that doesn't really exist. If you go over to Southern California, that doesn't really exist. It's pretty much desert. The same thing happens with the east and west side of South America. So where Peru is and Chile, you have the Atacama Desert. And this is due to the cold current versus over here we have lush rainforest. And that is all because of the warmer current. Neat, right? How that works out. So upwelling is also very important to our coastal areas and having cold and warmer water. So in coastal upwelling, here's our coast. Yes, I'm using props this time. Ooh. So here's our coast. With coastal upwelling, what happens is wind comes off, and it will essentially push the warmer top layers back, bringing up cold water. And this is known as Eichmann transfer, when wind pushes warmer water backwards, which causes or forces colder water to be pulled up. And this colder water isn't just chilly, it's also very nutrient rich, which means it's very good for the environment because it's good for the fish that are there. It gives them something to eat. Algae grows. And it is pretty chilly. So it will make sure that algae blooms don't exactly happen, but it's got a lot of nutrients in it that different organisms need. So remember, the wind is induced vertical movement, and coastal winds in combination with the Coriolis effect will cause this water to move away from shore, which is the Eichmann transfer. Okay, and I hope we all know what the Coriolis effect is. It's due to the Earth's spin and how it deflects wind. We're going to learn more about this a little bit in our meteorology section, but I hope you all remember what that is. Okay. So deep ocean circulation is a response to density differences in the water. So if you remember our last lecture about this, we talked about different reasons that density changes in water. One of them had to do with how much salt was in it or salinity. Others had to do with temperature, which would create thermohaline differences. You also have, those are the big two, so we're going to just stick with those. So this density difference will actually create dense masses of water as they cool and causes stratigraphy. So like thermohaline circulation or salinity circulation. And this causes downwelling of the water to just drop down. Okay. So basically the water in the northern polar areas is very cold and so much denser than the warm water that comes up through the North Atlantic gyre. So it'll sink down in the current as it travels south, and then it will warm and basically rise back up like a giant conveyor belt. And this will raise polar and temperate zones. This will change the temperatures in polar and temperate zones. So for example, in winter, it gets cooler down here, drier. That's because we're getting cold water from the polar regions. But then in summer, it starts to warm back up again. And so we're going to start getting those much warmer waters. It's very much a conveyor belt, and it is known as downwelling. Supplies, so remember, upwelling pulls up nutrient-rich water, downwelling causes the water to sink. So this supplies deeper oceans with dissolved gases, and at the equator, nutrient-rich water ends up rising. You can have wind-driven downwelling on the coasts, where the wind is blowing south along the west coast of the northern hemisphere for a period of time, which causes downwelling in areas often lower in nutrients and biological productivity. It's basically where you would normally have upwelling, you would have downwelling instead. So this global pattern is a very slow process, and it's important in the transfer of water and heat throughout the ocean. And this is essentially what it looks like. And this causes a lot of what we see in weather patterns. It's what we see in migration patterns for different groups of both mammals and fishy types. So, for example, the reason that great white sharks breed in certain areas is because of this. And it is pretty neat. So there are things that do affect our currents. One of them is fresh water being added in the polar zones thanks to the melting ice caps and snow. And the snow is normal. you're normally going to have in the summer, you're going to have the melting of sea ice. You're going to have the melting of snow and runoff. And this will always affect the temperature and salinity of the polar zones. Okay, this is a natural thing. However, the biggest worry is this new climate change issue, which is getting worse, not better, thanks to so climate change exacerbates this, so we get more runoff, more melting of, let's say, things that wouldn't have melted before. So now glaciers are starting to cleave. You're getting more icebergs, and these icebergs will melt, adding more fresh water. It's really not great. So, but in a normal stance, the normal addition of fresh water, thanks to snowmelt and runoff, can cause climate issues in Europe. So if you have a significantly more amount of runoff and freshwater addition to the polar zones, it will cause a greater issue in Europe that following summer, which does happen. Okay, you'll have wetter summers or drier summers, all based on how much snow runoff you have. So El Niños is when a southern oscillation develops, where trade winds diminish and then reverse. And the eastern movement of warm water along the equator starts to happen. And surface water of central and eastern Pacific areas become warmer, which increases the amount of storms they get, which means it's much warmer, wetter summers. Remember, the west coast of South America is a desert. So when El Niños happen, they have very wet, warm winters, which means they get desert blooms. This is part of why we get desert blooms in Death Valley in California, which is cool. And desert blooms are very gorgeous. I recommend taking a look at them. They turn into just huge, vast areas of color. La Niñas are when the normal circulation of water returns with vigor after an El Niño. This causes strong currents, powerful upwelling, chilly, dry conditions, and basically it leads to very cold, dry summers. This change in atmospheric circulation and weather patterns results in high atmospheric pressure zones, which will keep storms from their normal tracks. So storms that would have normally hit South America now are deflected north to Alaska, Washington, or even across to China and Japan and Indonesia. These are normal weather occurrences. They happen, I think, once every 4 years. So it's not this major issue. It is natural. It does happen consistently. Every so often you'll hear about it on the news when it does happen, and they'll show pictures of what's going on. But this is basically when California gets a lot of rain, because California doesn't get a lot of rain because desert. So shoreline. I know it seems like we're jumping here, but I promise we are not. Shorelines are a dynamic interface, meaning it changes constantly. They're constantly being modified by waves, storms, stream erosion, deposition of sediments, glaciation, volcanic activity, tectonic forces like earthquakes, and us. Human activity does change how coastlines work. So continental and oceanic processes will converge at the shore. Okay. This is where waves break. This is where you're going to have wind causing all these issues. Okay. So along the shore, let me change this a bit. Along the shore, this is where you're going to have, we all have heard of the drop-off zone. Basically, when waves hit this point, they can no longer continue their circular pattern that they make, and so they will crest and eventually run into the shore. And this in itself is a lot of force, so it will cause erosion over time, where maybe the shoreline will do this instead and change how it forms. This is also where you're going to see currents along the shore itself moving sediments. So eventually, maybe instead of that, you'll have an outcropping of the shore. And this is all just due to water movement. This doesn't have anything to do with us. It doesn't have anything to do with tectonics. That's just how it is. Now let's look at places like Hawaii, where you have a volcanic eruption, which will change the shoreline itself, because now we have new material being deposited, like lava, which will take a long time to break down, but it eventually will. But that's how you get an extension of a coastline, for example. So there are a lot of things that could happen. But this is also a transition zone between marine and continental depositional environments. So a river coming through may cause a delta, which will, let's say, increase how much sediment is deposited here because we are having something change. So now we'll have, instead of the coastline ending here, the coastline will end here, and you'll have a little bit of an outward push. Because there's a difference in flow. Now the river can't just keep flowing. It's just met resistance in the ocean, which we learned about in our rivers, or we will be learning about in rivers. But, oh dear. Oops, that wasn't supposed to be there. My bad. But there's a lot of damage that can be done at the shore because people like to live there. And shores are dynamic. For example, that's a person. That was a house. Because of shore changes constantly, this can lead to the destruction of personal property like a house, which is why insurance by the beach itself is actually pretty high, because this can happen quite often from storms or just from normal erosion. So waves are the energy traveling along the interface between the ocean and atmosphere. No, that sounds really weird. They derive their energy from motion and wind, and basically they are just how energy moves through the ocean a lot. Waves can be caused by different things. One of the big ones we talked about was wind. That's generally when you'll see most waves is with wind action. So there we go. Wind action, yes. So winds will cause more waves. So if you have a clear, calm day, you're not going to have a lot of winds. You won't have what we call choppy water. But if it is very windy, you will have what we call choppy water because it is causing friction against the water, which will lead to more movement, which leads to waves. So waves themselves are measured in different ways. We have wave height, which is the vertical distance between the trough and a crest of a wave. We have wave length, which is the horizontal distance between successive crests or troughs. We have wave period, which is the time it takes for one full wave to pass a fixed position. And then all three of these depend on the wind speed at the time, length of time that the wind is blowing, and fetch, which is the distance wind travels. As the wave travels, water passes energy in a circular orbital motion. And the frequency of the wave is the number of waves passing a fixed point. So if you have a higher frequency, the choppier your water is. So basically what you have is, here's the shore. Here's our water. Okay. We have a lot of wind. Okay. Our water will get choppier. This in turn will lead to a specific thing occurring. So water, as long as it does not reach the bottom, this wave will keep going until it hits the bottom. And once that happens, that's when you'll have a wave crest and break. Okay? Fun stuff. I know. So, here is the crest of two waves. So if we were to measure the distance between them, we would have our wavelength. Okay. Oops. Okay, and that gives us wavelength. The height is going to be the distance from the trough to the crest, and that's your wave height, okay? So, as long as you are below, okay, a depth of 1/2 of the wavelength, you will not have a waveform. But once you get to that, once this occurs where you have 1/2 of wavelength, this rotation can no longer occur. And that's what's important. This energy for wave movement is derived from wind. Okay, so you'll have higher waves due to this. This is our main way of making waves. Okay. Remember that waves are classified by their distributive force, which creates them, their restoring force, which tries to flatten them, wavelength, behavior, as it's influenced by water depth, speed, which is wavelength over period, and 3 factors will affect their growth: the wing strength, wind duration, and fetch. Okay, those are all very important. So, in order to make sure that a wave keeps going, its distributing force needs to be stronger than its restoring force. This behavior is then influenced by the speed or the wavelength over period. And again, strength, duration, and fetch. The wind is what affects it. Okay. Waves are unaffected by depth until they approach the shoreline, which is also known as the surf zone. They will begin to feel the bottom. And when water depth is equal to its base, meaning it can no longer complete a full rotation, it will basically trip on itself, forming a crest, and then go splat and basically break. Okay. Slightly faster waves that are farther out to sea will catch up and decrease their wavelength, which then causes the wave to grow in height. Okay. So how waves end up forming. Let's erase this so I can draw it a little bit better. It's kind of like you are moving with a huge mass behind you. Okay, so for example, pretend you have a large cape behind you. If you stop short, the cape will, instead of flying behind you, just kind of flip into you, right? The same thing happens with water. So here's your normal wave out at sea. Okay, once the rotation can no longer occur, the wavelength, will shorten, will shrink, which will cause a heightening of the wave and a heightening of the wave until it breaks onto shore itself. Okay. This means it is no longer able to support itself because its height has become too steep, causing it to collapse or break. Okay. When you are in surf, not surfing, surf, that means that you have some very turbulent water, meaning it's choppy. It's another term. Okay, so wave movement itself generally is unaffected by depth until it approaches the shoreline, basically here, shoreline, okay, which is known as the surf zone. At this point, the depth becomes less than 1/2 of the wavelength, and we start to see it touching the ground. So it's almost like walking on the ground. And as it does that, it's going to shrink and rise until eventually it cannot support its own height anymore and it breaks onto the shore itself. So, slightly faster waves that are farther out to sea will catch up and decrease their wavelength, causing a bigger height. So the slower the wave, the smaller the height. The faster the wave, the bigger the height. Okay, that means your difference between surfable and non-surfable waves. So surf is turbulent. Okay, when you are in the surf zone, it is the turbulent zone. This is where you're going to have the choppiest water. But in general, when water is choppy, you kind of bounce around a lot and it seems pretty rough. And there are different types of wave that we are going to learn about. One of them is the rogue wave. Rogue wave. Da, 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 da. These are freak waves which are due to interference and result in huge waves. And then you have plunging waves, which I may not have spelled correctly. And these are the ones that have huge, the iconic tube. These are known as plunging tubes. These are the ones that we know as surfer waves. Okay, remember that tube that we like to always see in those pictures from Hawaii. Then we have spilling waves. So spilling waves occur on a gradually sloping ocean bottom, like this one. This creates a crest that will slide down the base of the wave as it breaks. So it's pretty gentle. And then we have storm surges. I'm sure we're all familiar with that. Storm surges are a bulge of water driven on the shore due to things like tropical storms and hurricanes. And then we have the seichi. So seichis are long waves that occur in lakes or sometimes in an ocean basin that sloshes back and forth. This is known as a standing wave, and it essentially just goes back and forth and back and forth. And then we have tsunamis. And these are due to water displacement. So here's all the different wave types that you need. So tsunamis are due to water displacement, which actually have to do with earthquakes, and we're going to get back to that. So beaches are composed of whatever material is available. That means not all beaches are sand. And some have a significant biological component, but the material itself doesn't stay in one place. Basically, beaches move. But you have some beaches that are stone, some beaches are sand, some beaches are spiky because of the stones there that have been slowly eroded. But generally, not all beaches are the same, which we should know because Hawaii has black beaches. And again, beaches don't stay the same. They're not stagnant. They change. They're dynamic. And this is due to wave erosion. Okay, waves are important. Wave erosion is due to wave impact and pressure. Have you ever been hit by a large wave on the Atlantic coast of Florida? You know exactly what I mean. You feel a lot of pressure when you're hit with one of those waves, even if you dive underneath it. So this breaks down rock, slowly but surely, supplying sand for beaches. The abrasion is the sawing and grinding action of water armed with rock fragments, which allows it to be eroded. So for example, in Maine, you have beaches like this and all the way up into Canada. And then we have our sandstone cliffs, which, by the way, never stand underneath one of these. They will eventually collapse, and you do not want to be underneath that when that happens. So sand movement. Oops. All right, well, sand movement is what happens in the surf zones. And so what occurs here is that you're going to have movement parallel to a shoreline, like this, where wave energy causes sand to move perpendicular to the shoreline. And wave refraction is the bending of waves as waves first touch bottom in shallower areas. So instead of waves coming straight in, a lot of times they will kind of curve, which we should all have noticed. Sometimes beaches will curve in the direction of the longshore current. So waves will always arrive parallel to shore. Their energy will be concentrated against the sides and ends of a headland like this, okay, causing a straightening of irregular shorelines. So shorelines want to be straight, but what ends up happening is, thanks to longshore current, sand will eventually build up, which the waves will fight against, eventually moving sand as well. So this is another type of sand movement, longshore current, which does this. And this is why I was saying, like, it will cause the waves to deflect and move at an angle to shore, even though they're still technically coming in parallel. And then we have beach drift. Beach drift occurs as incoming waves carry sand at an angle up the beach, while water from spent waves carries it directly down the slope. So as they come in, it will carry sand this way, and then it will drag it back out. If you ever stand right where the waves come in and just stand there, your feet get covered in sand, right? And that is because sand keeps getting pushed up and dragged back, and pushed up and dragged back, and it catches around your feet. You'll also notice that the water right at shore tends to be very sandy. If you stick your hands in it, sometimes they'll come out feeling grainy. This is because, again, of the water pushing sand up and then dragging it back out. And this causes this sand that's being taken by the water to be moved along shore, which eventually will cause one part of shore to become narrower, and as buildup occurs, another part of shore to become bigger, eventually forming a headland. So erosion influences a lot of things along the shore. It will cause shores to narrow, and then deposition will cause it to widen. So erosion is influenced by local factors, such as proximity to sediment-laden rivers, degree of tectonic activity, topography and the composition, wind and weather patterns, and then just how the coastline looks on its own. So erosional features are wave-cut cliffs, wave-cut platforms, marine terraces, and headlands, which become sea arches and sea stacks over time. So this is a wave-cut platform. You can see how it has these ridges in it. This is where the water's been cutting and pulling and cutting and pulling just because it's a shoreline, so it's causing waves to break there. And then this is a marine terrace. It's kind of almost like a cliff. And it's pretty tall. You see in a lot of pictures in Ireland, it's pretty. And so this is a sea stack and a sea arch, which I'm sure you all watched How to Train Your Dragon in the beginning, when Hiccup finally gets on Toothless, and they're flying around. They end up flying under a sea arch. So sea arches eventually wear away thanks to salt, wind, and water erosion and become sea stacks. Which means that they're separate from the land. And these eventually do just kind of wear down and wear down and wear down. But this rock that is over here is usually going to be something like sandstone, which is easy to wear away, or limestone. All right, depositional features involve a spit, which is a ridge of sand extending from the land into a bay with a hooked end. Baymouth bar, which is a sandbar that is so large it crosses the bay completely. Then you have tombolos, which are ridges of sand that connects an island to the mainland or another island. You have barrier islands, which form mainly along the Atlantic and Gulf coasts. These run parallel to the coast and can originate in many ways, including being spits severed from the mainland, turbulent waters heaping up sand, and former sand dune ridges that originated along shore but kind of moved. These will be the storm break. They will protect us on the mainland from harsh storms, but they are supposed to. So here is a baymouth bar. Okay, this is what happens when a sandbar will cover an entire bay. This is a spit. Again, it looks like a hook. We have two of these. We have one in Cape Cod, Massachusetts, and we have one in Sandy Hook, New Jersey. These are, if you don't know, off the coast of South Carolina. We have a bunch of barrier islands that are very popular. This is Hatteras Island. Okay, these are barrier islands. They are intended to protect the sound from huge storms, except they have become very popular living locations. And here we have a sea arch, a tombolo. So these all form. So at first you had an island and let's say a sea arch. Okay. As time goes on, your sand is becoming up and down, up and down. It will catch, for example, right here, and it will catch right here. Maybe it's a little bit shallower there, which will result in a spit and a tombolo now connecting the island to the mainland. Okay. This sea arch, however, has now been eroded, leading to a wave-cut cliff and a sea stack. Over time, as the longshore current keeps going, The spit will become a baymouth bar or island, and tombolo will disappear thanks to erosion, which will lead to a wave-cut cliff. A new spit will form in this little inland that's about here, which is basically where the tombolo went. And you'll start to get beach deposits over here by the original wave-cut cliff, because again, it's still shallower there. It's where it's going to catch. So coastline erosion is different for the East Coast and the West Coast. So on the East Coast, shoreline erosion is based, shoreline classification is based on changes with respect to sea level. So you have emergent coasts, which are either uplift of the land or a drop in sea level, and then submergent coasts, which is when land subsides, so it sinks, or the sea level rises. Features include highly irregular shorelines and estuaries, which are drowned river mouths. We have estuaries all over Florida. And that's a submergent coast. Okay, this is what we have. Okay, and this will cause erosion on the east and Gulf Coast, which usually affects barrier islands. They face the open ocean and so receive the brunt of basically everything. And developments have taken place more rapidly since now we understand barrier island dynamics. So, for example, we had this lighthouse, and they have been trying very hard to protect it, thanks to building groins and beach nourishment. But eventually, they had to actually pick up and move the lighthouse inland to save it. And you can go see this lighthouse. It is pretty cool. It's very pretty. Fun fact, all lighthouse patterns are different. It's what describes each lighthouse, and it's how you are able to mark where you are on the coast. So in the Pacific coast, erosion is very different. Their coastline is marked by very narrow beaches backed by cliffs or mountains, because remember, we have the Cascades right there. These are all volcanic. They're igneous. They're going to be very resistant to erosion. However, these beaches, they're not getting replenished, okay, because you have rapid erosion, especially thanks to those mountains. They don't have a lot of sediment coming off of them to help replenish beaches like we do on the East Coast. So the major issue here is the narrowing of beaches. So sediment for beaches is interrupted by dams and reservoirs that have been created because, we need water in California. And this results in rapid erosion. And this is bad for places with steep cliffs which erode underneath and then collapse, like in Los Angeles, where we actually see houses falling off into the ocean itself, which is kind of sucky, but I chose to live on a cliff. And this is what the beaches in California and Oregon and Washington basically look like, which is really cool. And it's all because of these mountains. Okay. There is not a lot of sedimentary runoff from them. We also have dams preventing a lot of runoff heading into the ocean here. So responses. We obviously want to keep our beaches from going away. So we have created hard stabilization, which are groins, which are barriers built at right angles to the beach, which trap sand. We do have these in Florida. You'll see them all over the place. They're these huge concrete structures that go straight out into the water. I'm sure you've seen one before. We have breakwaters, which are barriers built offshore, parallel to shore. And these are not that effective. Groins are the most effective in my opinion. They actually catch sand. And then we have seawalls. They are the armor of the coast. The idea is that waves will break against them. And if you haven't seen pictures of Maine, you can look up Maine seawalls. They're all over the place. They look really cool. They look like a whole bunch of stones piled up. And that's the point, is that it'll protect the shore because the waves will smack against the stone rather than against the shore. It makes a nice spray of water. It's pretty. But again, it's not really that effective either. So these are groins. We see these, again, all over in Florida on our beaches. They do kind of work. Probably the most effective if you're going to look at all of them. This is a breakwater. It will protect this. It will protect docks. And this causes a disruption of the longshore current, which means that sand will kind of build up over here, which is nice. And this is the seawall I was talking about, where it's basically just a pile of stones that creates a nice spray of water. Again, really not that effective. All right, alternatives are beach nourishment and basically relocating buildings away from the beach. Basically, please do not live on the beach. Beach nourishment is when we dredge offshore sand and then put it on land itself. And this is where we're going to get a lot of our really pretty seashells. Fortunately, it's going to lead to disruption of the biology out there, but we get our beaches. And then we have the tides. Tides are very important for the beach, as I'm sure we all know. And tides are really affected by the moon. The moon's gravity will attract the oceans towards it, forming a bulge. Basically what this does is everything kind of does this. And this is why we have the bulge. So it's not like all of the water is just going straight towards the moon. It's kind of getting pulled towards one central point, which happens to be here. And so that's what's going to cause this nice bulge on either side, because on the other side we're going to have a resulting tidal bulge. And so this is really affected by the moon, because the moon has a slight pull on the Earth, just as the Earth has a pull on the moon. So combined with the motion of the Earth, we have two bulges that form along the equatorial region, which vary from pole to equator on either side of Earth. And tides are generally 24 hours and 50 minutes long, which is, believe it or not, a lunar day. Fun fact, make sure you remember that. So therefore, tides occur later each day with 8 hours between each tide. And tides are the longest of all ocean waves, and they are formed by inertia and gravity. So high tide, which remember I told you we talked about tsunamis and how tsunamis affect stuff. Well, there is a place where tides cause a really interesting effect. For example, in the Bay of Fundy in Nova Scotia, which is known as Minas Basin, you get a tidal flat. And a tidal flat is when at low tide, everything goes out. And so this is one of those instances where the water disappearing is okay, versus with a tsunami where it all goes out and you're like, oh no. In this situation, it's okay. However, the water does go out very slowly, but it comes in very fast, like 2 times as fast, okay? So you need to be out of there by the time the sign says to, or you can get very hurt. Cool things here. We can see how high water level can get based on the erosion lines. But yeah, you can go out entirely, wear special shoes for that because it is very muddy. And you can actually go out and walk on the ocean floor. It is neat. This right here is a feature we learned about earlier. Which, if you don't remember, go back and look it up, because that might be the question for this lecture. So slide 38, what is this called? Ooh, make sure you answer that, because that's totally the question now. Where was I? So yes, this is Minas Basin. Which is pretty neat. I definitely recommend going there if you ever go to Nova Scotia. But monthly tidal cycles occur because the sea is a she. Haha. So spring tide occurs during the new and full moon. Okay, very important. The new and full moon makes the spring tide. Okay, this causes the bulges. And it's when the moon is aligned at where these bulges are, and so you'll have a very large tidal range. You'll have your highest high tide and your lowest low tide. Versus with your neap tides, it's going to be a little different. With your neap tide, you're going to have the first quarter and the third quarter moon. Okay, and with neap tides, Neap tides are going to cause the least difference. So you're going to have a very little difference between high and low tides. Okay. So remember, spring tide, highest tide, lowest low tide. You're going to have the greatest difference between the tides. Versus neap tide, where you're not going to really have a difference between them. You're going to have a tiny high tide and a tiny low tide. There are many factors that influence tides, not just the moon. The shape of the coastline, the configuration of the ocean basin, water depth. And so you have three major patterns out of this. You have diurnal tides, where there is a single high and low tide each day. Okay. This occurs along the northern shore of the Gulf of Mexico. You're going to have semi-diurnal patterns, which effectively have two high tides and low tides each day. And then you're going to have very little difference between the high and low tides. And then we have the mixed pattern. So the mixed header pattern is when you're going to have two high and two low each day. And there are large inequalities with the high and low water heights or both. These are what you're mostly going to have along the Pacific coast of the United States, where you could have a super high tide and then a very little low tide, or a kind of low high tide, but a very large low tide. So what we have along our side of Florida is actually a mixed tide. So we can get some really high tides and then not really low tide, or we could have a super low tide and then have a high tide. Versus the west coast of Florida or the east coast of Florida, we'll have the semi-diurnal, where you have two high tides and two low tides per day, but they're not incredibly high or incredibly low. Neat stuff, right? All right, so tidal currents are the horizontal flow accompanying the rise and fall of tides or tidal waves. This is the rise and fall of sea level as the tide crest approaches and passes. The flood current is when water advances into the coastal zone. Ebb currents are when you have seawater moving water seaward. So flood current moving in, ebb current moving out. Kind of like a flow and ebb. So if we were to draw a picture, okay, so here's our shore. Okay, here's our shoreline, and here's our water. So our flood current is going to go onshore, and our ebb current is going to go back towards sea. So the water is going to go away, water comes in, water goes out. Flow, flood, ebb. Okay. Tidal flats are areas that alternatively get covered and uncovered by tides. These can lead to tidal pools, which are pretty cool. These are baby nurseries for fish and other sea creatures, and you can find a lot of cool stuff in there. We don't have a lot of tidal pools in Florida, but you can find them, I think, in Georgia and South Carolina. I know we have a ton in New Jersey. Tidal deltas is when water breaches a barrier island landward. All right, and so this is our tidal delta. So basically what happens is you have this barrier island and we have waves coming in, and eventually it will break through the barrier island itself. And it will actually drag the sediments out with it, forming this sort of delta. And so remember, lagoons are behind barrier islands. They're generally going to be calmer, warmer. You're going to have a lot of sea life hiding in here, which makes for great fishing. You're also going to have possibly coral reefs occurring. Moana was a great example of an area which had a lagoon. And then this tidal delta, these sediments can eventually be dragged on land, forming these tidal flats, which is super cool. All right. So that is our lecture. Please remember to put all your questions on the Canvas discussion board. Have a great day.